So as we begin our new lesson, let's think about the common ion effect. When we have two solutions, each with an ion that's in common, we'll look at that as the common ion effect. And one of the first examples reads, when we have a salt with an ion of a weak acid, it reverses the dissociation of the acid, and it literally does so by lowering the percent dissociation. Now let's make sense of what the sentence is saying. Let's say that I have a weak acid. We're going to call it HA. And the very definition of it being weak, it's giving us an equilibrium where we have H plus and A minus. Now, according to Le Chatelier's principle, if I have another salt, if we're looking at a salt with the same last name as this acid, so let's say that this was acetic acid, and so over here, let's say my salt was sodium acetate, so I have the same last name, then we would be applying a stress, adding an ion that's in common with this same last name. So let's say I had sodium acetate, and we'll just call that Na. So I have my Na plus and A minus when it dissociates. So I have extra, I'm adding stress, so I'm increasing my A minus. So that means Le Chatelier's principle is going to push my equilibrium to the left, which is going to use up or draw out my H plus ions, making this less acidic, which is going to increase the pH of the solution. So the same principle applies to salts with the cation of a weak base. So let's use some general chemistry here. Let's say that I have a base put into water, and we have BH plus formed and OH minus formed. So it's telling us if we put in a salt who has the same first name as the base, say ammonium chloride, or let's see, thinking of something that's in common. Well, the stress says that if we are increasing our BH plus, then we are shifting our equilibrium left. Again, so we are removing, we're using up that OH, which is making it less basic, so more acidic, so it's lowering the pH of that solution. So the common ion effect says, so we're going to be studying an acid-base equilibrium. So we're studying some sort of equilibrium, and then really according to Le Chatelier, we cause a stress, and the stress is putting something in common with it and watching it shift from left to right or right to left, but then calculating this based on an ice chart. So as we consider the approach when we are solving these problems, we need to identify the major species in solution, consider their acidity or basicity, identify that equilibrium, and then really look at that equilibrium aspect of the ice chart. So let's look at an example here. Question number 1 says, what's the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate in enough water to make a 1 liter solution? And we're given the Ka of 1.8 times 10 to the negative 5. Well, let's look at the chemistry here. We're told that we have acetic acid, which is a weak acid. And the very definition of a weak acid says that it sets up an equilibrium. And it will do so by creating ions of hydrogen and acetate. So let's write this out here. We have HC2 and our Ka given is 1.8 times 10 to the negative 5. We're also given that we have a salt. We have sodium acetate. So we have Na C2H3O2. And a very definition of a salt says that there is not an equilibrium. It's a strong electrolyte. So it's going to dissociate into Na plus ions and acetate ions, and it's going to 100%. So we're told, since it's 0.3 moles in 1 liter, so we have 0.3 molar sodium acetate. That means when it 100% dissociates, we're given 0.3 molar of sodium ions and 0.3 molar acetate ions. Now what we care about here is our acetate, because that is what is in common with our weak acid that's in equilibrium. So if I look over and set up my ice chart for my weak acid, I also can see that my initial concentration, I have 0.3 mole of acetic acid, and I know that I have 0 and 0 plus, since here's my common ion effect. Over here I started with 0.3 molar of that common ion, the acetate. So down here, my change, we know as time goes by, we lose acid and we gain product. So this would be 0.3 minus X. This would be X. And technically this would be 0.3 plus X. So here's where the math gets a little easier though. We're going to assume that 5% rule, and we're going to toss out the plus X and the minus X. So in other words, when we are looking at the amount of acetate ion that's being contributed to this equilibrium from the weak acid, compared to the amount of acetate ion coming from the salt, it's negligible. It's not worth adding into the math. The Ka simply becomes products over reactants, and look what happens. So we have our Ka is equal to our products, so X times 0.3 molar over my acid of 0.3 molar, and the math simply shows these canceling out, and X becomes the Ka of our weak acid. Remember, we let X stand for hydrogen ion, and the negative log of that value, we get our pH. So we can see here that our negative, or 0.3 and our 0.3 cancel out, so X is equal to 1.8 times 10 to the negative 5. So let's plug in our negative log of 1.8 times 10 to the negative 5, and we should get 4.74 for our pH value, which would make sense knowing that it's a weak acid. So let's go back and look at what we did. The pH of a solution, if we have 0.3 moles of acetic acid and 0.3 moles of sodium acetate. So we know that our acetic acid is a weak acid. We set up our equilibrium because we know that a weak acid forms an equilibrium, and we're given the equilibrium constant. Sodium acetate, however, is a salt, and by definition, 100% dissociates. So we know that if I have 0.3 molar of my sodium acetate, I have 0.3 molar of acetate. And acetate is a common ion with my acetic acid conjugate base. So by Le Chatelier's principle, if I have a stress, so I have extra ions here, we're going to shift this equilibrium left. All right, so I'm going to set up my equilibrium constant. So what I added here, instead of having 0 and 0, like I normally would, if I did not have that other piece, we would have 0.3, 0, and 0. And then we would have minus X and plus X. Remember when we would set up this equilibrium, we would have X times X, right? But I added that 0.3 molarity extra acetate. That was a stress on this. So we have 0.3 M times X. all over 0.3. And that makes our math was easy in this case. It's not always the case like that. So we have those cancel out. We have x was 1.8 times 10 to the negative fifth. Our x represents our hydrogen ion concentration. And we know that if we do the negative log of x, let's look at another example here. We want to calculate the pH of a solution containing 0.085 mole nitrous acid, and we're given the Ka value, and 0.1 molar potassium nitrate. So let's write out, we know our nitrous acid is a weak acid, so we have HNO2. And again, definition of the weak acid is that it forms an equilibrium, H plus and NO2 minus. And we have our Ka of 4.5 times 10 to the negative fourth. We're also told that we have potassium nitrite, KNO2. And again, this is not forming an equilibrium because potassium nitrate is a salt. It will 100% dissociate into K plus ions and NO2 minus ions. So we were told that we have 0.1 molar concentration of potassium nitrate, which means we have 0.1 molar of K ions and 0.1 molar of nitrite NO2 minus ions. So we can see our common ion that we have here is our NO2 minus. So we have a greater concentration of that. Again, Le Chatelier say that if I increase here, we're shifting left. So let's write down our HNO2, we're told is 0.085. Right? So we're going to lose. So we're going, and we have 0 initial, and then we did have 0, except for we don't have 0 NO2 minus. We have 0.1 molar of it to start with. And so again, we're going to minus x. We're going to plus x plus x. So we would have 0.085 minus x. And then for our hydronium, we have x, and then 0.1 plus x. And again, we're going to assume the 5% rule, and that x is so negligible that we can take that minus x and the plus x and just cross them off. So then we're left with our Ka, our 4.5 times 10 to the negative fourth, is equal to our products over reactants. So 0.1 times x over 0.085. So if we simplify here, I'm going to do 4.5 times 10 to the negative fourth times 0.085, and then divide by 0.1, and I get x is equal to 3.825 times 10 to the negative fourth. Now remember, our x is our H plus concentration here, right? X and x. So I can do the negative log of 3.825 times 10 to the negative fourth to get a pH. Negative log of 3.825 times 10 to the negative fourth to get a pH of 3.42. So very similar to the ice tables we did in the previous unit. The only difference is that we are adding this common ion. So we are initially starting with more of a product on the right, so therefore it's shifting our equilibrium left and affecting the pH. Let's look at another example here. Here we want to calculate the fluoride ion concentration and pH of a solution. So we've got HF and we have HCl. Okay, so let's write HF is not a strong acid. So it sets up an equilibrium, gives us H plus ions and F minus ions. Then we have HCl. And HCl is a strong acid, does not set up equilibrium. It 100% dissociates into our H plus and Cl minus ions. So we were told that we had 0.1 molar of it. So 0.1, 0.1, 0.1. And notice here that our common ion in both of these is our H plus. So let's look over here, our HF, since it's our weak acid, we do need to look up our Ka value for that. So I'm going to get out my Appendix D and look up Ka, and we see that it's 6.8 times 10 to the negative fourth. All right, so we're told that our HF, that we have 0.2 molar HF. And again, we know that we started out with so initially 0 plus 0.1 molar, since this is my common ion, 0 plus 0.1, and again, 0 of my product. And then we're going to minus x, plus x, plus x. So at equilibrium, we would have 0.2 minus x, 0.1 plus x, and x. So again, we're going to just start assuming from here on out that these little minus x's and plus x's are nulled and voided. So we could actually even simplify our ice table from here on out. We can just go, okay, what we're starting with is what we're given. We know that it's going to be the concentration of the common ion, and then instead of 0, since we're adding x, and then the other ion is x. All right, so now we can set up our Ka expression here. So Ka is 6.8 times 10 to the negative fourth, which is equal to our product, so our 0.1 times x over 0.2. And let's solve for x. So 6.8 times 10 to the negative fourth times 0.2. And we're going to divide that by 0.1. So x is equal to our F minus, our concentration of our F minus, actually. So that's going to give us our fluoride ion concentration, which is 0.00136 m. Now, to find our pH, remember pH is the negative log of our hydronium ion concentration. And we know our hydronium ion concentration. This common ion right here are 0.1. So the negative log of 0.1, I have to plug that in here, negative log of 0.1. Oh, we get a pH of 1. pH of 1.00. Remember, we go to 2 decimal places. So in this case, our common ion was actually the H+, giving our fluoride the X. We didn't know. So we were able to pull out our fluoride ion concentration and then go back and calculate our pH, knowing the hydronium ion concentration. Let's do another. Here it wants us to calculate the formate ion concentration and the pH of a solution that is 0.5 molar in formic acid, and it gives us our formula here. So it's HCOOH, and it's given us a Ka, so we know that's a weak acid. We know that our weak acids form an equilibrium. In our equilibrium, this is our acidic hydrogen, right? So we have H plus and HCOO minus, and our Ka is 1.8 times 10 to the negative fourth. And then we're also given 0.1 molar nitric acid. So our nitric acid is HNO3. And remember, nitric acid is one of those big seven, where it 100% dissociates. It is a strong acid into H plus and NO3 minus. So we're told we have 0.1 molar. So 0.1 molar of nitric acid means we have 0.1 molar of H plus ions and 0.1 molar of NO3 ions. So here we can see our common ion is our H plus. So I know that I'm starting off with 0.1 molar of H plus. It also tells me I'm starting off with 0.5 molar of my formic acid. And so that leaves my formate ion concentration as our X. And again, we would have had minus X and plus X over here, but we're assuming that 5% rule. So now let's set up our Ka expression here. We would have 1.8 times 10 to the negative fourth is equal to my hydrogen ion, my 0.1, times my formate ion, X, all over my formic acid, my 0.5 molar. So let's set this up. 1.8 times 10 to the fourth, 10 to the negative fourth, times 0.5, and divided by 0.1. So my formate ion concentration is 9.4. So X, which is our formate, HCOO minus, concentration is 9 times 10 to the negative fourth molarity. And then to calculate the pH, remember the pH is the negative log of my hydronium ion concentration, which we know is 0.1. So the negative log of 0.1, and we just actually looked that up. And plus we know that this is 10 to the base units, right? So negative log of 0.1 is 1. pH of 1.00. So if we flip our page over, we are wanting to summarize what is the common ion effect. Well, if we think about it, it's the extent of ionization of a weak acid being affected by the addition of a strong electrolyte of some kind of salt with an ion that's in common. So let's begin to write some sort of a succinct sentence. Here we go. So I wrote down the extent of ionization of a weak electrolyte that is decreased by the addition of a strong electrolyte that has a common ion. Now let's give an example of a salt that can decrease the ionization of HNO2 in solution. So we know HNO2, nitrous acid, is weak. And if we think about the Bronsted-Lowry equilibrium, that sets up a equilibrium forming nitrite and hydronium. So we have our conjugate base, which is our nitrite, and our hydronium, which is our conjugate acid. Now, here we're saying we need to give an example of a salt. So a salt is looking at not an acid, not a base, but using this conjugate base as our last name and using a different cation attached with it. So we could say lithium nitrite. We could say sodium nitrite. We could say potassium nitrite. Any of these are strong electrolytes, meaning they will 100% dissociate. Again, this is not an acid or a base, but it has a first name cation that is not H, it's not an acid, it's not a base, strong electrolyte. And so let's say I were to choose sodium nitrite, NaNO2. And we can see that these both have the nitrite in common. So here I've got nitrite, I have lots of nitrites. So I have an increased number of nitrite. And Le Chatelier says, well, if you've increased it, I want to decrease the nitrate. And to decrease the nitrate, we're going to shift this equilibrium left to use up the nitrite. So how do we decrease the ionization? Well, we need a strong electrolyte with the same common ion as my conjugate base. So in order to do that, that will help us decrease the ions as we shift our equilibrium towards the molecular form of the nitrous acid. Again, our ions are on the right. If we have a common ion, then we mix it with that salt that has a common ion. That means we have increased our ions. Le Chatelier says if you've increased it, we're going to use them up. We want to decrease it. That's the response to the system. And so it shifts our equilibrium left, decreases the ions to create more nitrous acid. This next part wants to know if the pH increases, decreases, or remains the same when each of the following is added. So we have NaNO2, which is a salt, right? Sodium nitrite. So this is a salt. You know, that's a strong electrolyte. And then we have HNO2, and we know that that is a weak acid. This is where my equilibrium lies, right? So if I have my HNO2, just like what we did up there, I'm just not going to include the water. We know that there's an equilibrium forming my H plus ions and NO2 minus. And we see that our common ion, the NaNO2, so if I increase my NO2 ions here, because we know that NaNO2 is going to 100% dissociate, so I will have NO2 ions and more added to NO2 ions, so that is going to increase my NO2 concentration, right? And what is the response? The system response was, wow, there's a whole lot of NO2 ions. We need to use them up. We need to decrease the NO2 ions. So my system shifts to the left. What that also means when it shifts to the left is that it wants to decrease those NO2 ions. It also decreases my H plus ions. So there will be less H plus. And what does that mean if I have less H plus? That my system becomes less acidic or more basic. So my pH will go up in the number line. If it became less acidic, becoming more acidic lowers the pH. Less acidic gets higher or more basic. This next one, we have methylamine chloride, CH3NH3Cl. And we can tell that this is our salt, right? Because it's a chloride. Like we know sodium chloride is a salt. And then we have methylamine. So if you were to look at, and you wouldn't need to know these names, but we could look at our Appendix D, and we would see that the CH3NH2 is a base. It's a weak base. And it has that nitrogen, which likes to attract those hydrogens. So let's look at the chemistry here. When we have our weak base and we put it in water, so we have our CH3NH2, So a weak base forms an equilibrium, and we know that this base wants to grab a hydrogen off of that water. So CH3NH3 plus is the one ion it dissociates, and OH minus, that leaves that water. That water donates one proton, so we're left with OH minus. Now, when we look at adding our salt, our CH3NH3Cl, we know that when we have a salt, it's a strong electrolyte, it 100% dissociates into the CH3NH3 pluses and the Cl minuses. So our common ion here, we can see, is our methylamines, CH3NH3 pluses. So we are increasing this amount, which Le Chatelier says if we're increasing those ions, we need to decrease those ions. We need to use them up, shift this left. Now that also means that these hydroxide ions will be removed. They will be used up just like these are being used up. So we are removing hydroxide ions, which makes this less basic or more acidic. So therefore, pH here is going to decrease. For this next one, we're told sodium formate added to a solution of formic acid. And again, you wouldn't be expected to know these, but you could look them up in Appendix D. So we would see that formic acid is a weak acid, and formic acid is HCHO2. So if we added our formic acid in with water, it's going to form an equilibrium, and it's going to make formate. So again, our formic acid is our proton donor, so we would have CHO2 minus, and it's donating that H to our water to give us H3O plus. And then we would look up sodium formate, which is NaCHO2. And so therefore our common ion is our formate, because Na is plus and CHO2 would be minus. So we are increasing our formate ion concentration, which again is going to shift left. So it will use up our hydronium concentration or remove it. But that means our H3O concentration goes down. And if H3O goes down, that means we're less acidic, right? So if we remove the hydronium concentration, we remove that, it's becoming less acidic, more basic, pH goes up. Let's look at potassium bromide. This is our salt, hydrobromic acid. So hydrobromic acid, we should know that's one of the big seven. It 100% dissociates into H plus and Br minus. So there is no equilibrium for strong acids. And if we were to look at potassium bromide, potassium's parents would be KOH or HBr, which are both strong. Therefore, there's going to be no effect on the pH. And let's look at this last one. We've got HCl added to a solution of sodium acetate. Let's look at HCl first. HCl we know is a strong acid. And so it's going to 100% dissociate into H plus ions and Cl minus ions. And then we have sodium acetate. So let's look at NaC2H3O2. Well, so when it splits, this is a salt, so it's going to form our Na plus ions and acetate ions. Now notice we don't have any common ions, so we're not actually looking at common ion effects in this example. But let's see if the pH will be affected at all. If we were to look at the parent of Na plus, that would be NaOH, and that is a strong parent, so that's not going to have any effect. But if we looked at the parent of acetate, which is acetic acid, we know that that's a weak acid. So if we looked at the hydrolysis of C2H3O2 minus in water, we know that, again, acetic acid forms an equilibrium. We get the parent acid, the acetic acid, HC2H3O2, and OH minus ions. So we know that these OH minus ions are the base ions. And so we have our hydrochloric acid, which is 100% forming our H plus and our Cl minus. But notice that when I add the sodium acetate, that it releases base ions. So here I've got H ions and I've got OH ions. So it's going to, these OH will consume some of those hydronium ions. So if it's removing those to form HOH, to form some water molecules, then that means that we are, if we're removing H plus, that means we are becoming less acidic or more basic or increasing the pH. So again, not a common ion effect, but we can still look and see what sodium acetate does. And the sodium parent, be it sodium hydroxide, did not have effect on it, but the acetate forming acetic acid and hydroxide, that hydroxide does have an effect on it.